We use a chi-squared test for independence when we're trying to decide whether two categories or two qualitative variables are independent or dependent on one another. Okay, so the chi-squared test of independence just helps you provide evidence to see whether, in this case, looks like the subject, see whether the subject is dependent on whether a student is an athlete or not. Okay. So a survey asks a group of college students about their majors. It also groups the students by whether they are athletes or not. So if we're going to run a chi-square independence test, we're going to test to see whether a person's choice in major is dependent on a person's status as either an athlete or non-athlete. Okay, or maybe they're independent, maybe they don't affect one another. So for this problem, we don't actually have to do the null alternative hypothesis. I've got another video for calculating test statistics too, but they want to know which one of these tables are set up so that you have the expected values correct. Okay, that's just to help us in notation. We usually put the expected value right underneath each observed value. So they expect, like for this table, if we expect 11.5 athletes to be also humanities students, that's what we put here. So that might be wrong though. We need to calculate the expected values ourselves. So the way you do it is you find out the probability of like assuming that they're independent of each other. Assuming we start off with this null hypothesis of independence, and then we're going to calculate a test statistic. We won't do it for this video, but later on we'll calculate a test statistic to decide whether they are dependent. So we're going to assume HO is true. We're going to assume that they're independent of one another. And we're going to find the probability that a randomly selected student would be an athlete and a humanities student, and then multiply that probability to the total amount of students. In other words, it's like the expected values that we did earlier on in the course. You take a probability and then multiply it to the actual value of X. So the way we can do that, kind of short description of how you calculate each expected value, is you're going to take the row total for, like, let's start with athlete arts. Take the row total, multiply it to the column total, and then divide it by the grand total. Okay, so the row total is 36, the column total is 35, and the grand total is 75. So if you multiply 36 times 35, then divide by 75, we expect 16.8 students to be athletes if they are in the arts in this sample. So assuming they're independent, if you have 75 students, we expect 16.8 of them to be arts and athlete students. And that might be enough to eliminate them. Like, this is 15.8, 17.8, 17.8, 16.8. That's the only one with 16.8. So you really just have to calculate probably one or two expected values. Like if you got 17.8 for arts and athlete for an expected value, then you'd have to do another calculation. But you don't have to fill out the whole total. Okay? You know, as you've got the idea if you can get one of the values. But let me just double check that again. Row total times column total divided by the grand total. 16.8, yep, that's the only one that's got it, so that's got to be our correct answer. Okay, sorry, I always cut the video off. I never know when there's going to be more than one part in Newton, but the first part of this problem, we were supposed to find the expected values for each of these cells in the table. Okay, luckily we found one, and that was enough to eliminate all the other options. So this is the expected value. So to calculate the test statistic, which I think is the next part here, yeah, the test statistic is going to sound familiar to the goodness of fit test if you did that before. Okay, so here's my poorly drawn chi-square symbol. To find the test statistic, you sum up the observed values and subtract it by the expected values, square that difference, and divide by the expected. Okay, so yeah, we got it. Oh, it's actually going to be easier to look at this table up here because you've got the observed value right here. The first one is going to be 17 is what we observed. 16.8 was what we expected when we calculated that expected value. and then you need to divide by the expected value for that cell. So that's for this first cell right here. Okay, for the next one, for humanities, we're going to put a plus symbol because we add them all up. Take the observed value of 10, subtracted by the expected value of 12.5, square the difference, then divide by 12.5. And then keep going until you've done it for all 6 of these cells. Remember, don't do it for the totals. Okay, so to save some time, I'm going to do each one separately with a calculator. 17 minus 16.8, square that, divide by 16.8. Oops. First one, oh man, nice and yucky. Oh, from another video. That's what we got for that first fraction. Second fraction, 10 subtracted by 12.5. Square the difference, then divide by the expected. That's nice and clean. And then we got 9 minus 6.7. Square the difference, then divide by that expected number on bottom. We got 18 minus 18.2. Square the difference. Oops. Square the difference, then divide by 18.2. I'm going to round that up to 2. Observe minus expected squared, divide by the expected, 0.463. We got observe minus expected squared, divide by the expected. So 0.725, we'll say. Okay, add all those up and you get your test statistic. We got 2.48, kind of a low test statistic. Oh, what was it? 2.48, so 2.5 when you round. Let's see if there's another part for you. Oh, that's it. That's it for that video. If there was another part, it might say like compared to a critical value, which is the same thing as what we did in another video when we conducted a chi-square test. Oh, what did we do? Test for goodness of fit. Okay.